When an object strikes a solid floor, the reason it cannot penetrate the surface is found in quantum mechanics. The same principles that govern the atom are responsible for the existence of permanent magnets and the conduction of sound through a steel beam. The Pauli exclusion principle dictates that two identical electrons cannot occupy the same quantum state simultaneously. When the electrons in your feet press against the floor, this prevents them from overlapping, creating the physical resistance we experience as solidity. To model how these objects behave, classical physics relies on the Hamiltonian framework, a system of equations that assumes every particle has a perfectly defined state. In this model, we map a particle's position and momentum on a grid called a phase space plane. Every physical state is represented by a single, infinitely sharp phase space point. As the particle moves, this coordinate point traces a continuous trajectory, allowing total prediction of the system's past and future. Quantum mechanics proves this precise coordinate point is mathematically impossible. The transition from classical to quantum physics marks the end of the clean, predictable trajectory at every scale of the universe. A common misconception suggests that uncertainty occurs because a measuring device, like a photon from a microscope, physically bumps a particle and changes its path. This implies the uncertainty is an experimental error. In reality, even an instrument with infinite precision and no physical impact would encounter the same limit. We define delta x as the standard deviation of a quantum mechanical probability distribution. This curve is derived from the Schrödinger equation, which describes the state of the particle itself. This variance, the square root of the average of the squares minus the square of the average, is intrinsic to the state. It exists before any measurement is attempted. External noise from thermal vibrations or outside perturbations can increase the spread of your data, but they sit on top of a baseline uncertainty that remains even at absolute zero. This baseline is expressed by the inequality. The product of the uncertainties in position and momentum must be at least Planck's constant over 2. This limit applies specifically to canonically conjugate pairs, variables where the classical Poisson bracket is replaced by a non-commuting quantum operator. If the variables are not conjugate, such as a particle's position on the x-axis and its momentum on the y-axis, their commutator is 0. These properties can be known with infinite precision at the same instant. The uncertainty principle is a geometric law of nature governing how conjugate properties can coexist. By plotting the uncertainty of position against momentum, we visualize reality's boundary, a rectangular hyperbola. In most natural states, the system sits in the region above the curve. The area beneath is prohibited. No state can occupy this space. By isolating a system from its environment, experimentalists can slide a state down the graph until it reaches a minimum uncertainty state on the boundary. If we squeeze the state to reduce position uncertainty toward 0, the hyperbola forces momentum uncertainty to climb toward infinity. These squeezed states are used in quantum optics to achieve extreme precision in one variable by deliberately sacrificing knowledge of its conjugate. Because length and momentum have different physical dimensions, we use dimensionless variables to identify the optimal, symmetric point on the curve where the error in both is equally minimized. This confirms that a particle in phase space is never a point. It is an irreducible, fuzzy area of a minimum size determined by Planck's constant. As this fuzzy area moves through time, it distorts and spreads, making the classical concept of a precise, infinitesimal trajectory impossible to maintain. Every physical state occupies a minimum geometric volume of inescapable fuzziness. The classic Bohr model depicts an electron on a precise circular track. Existing here requires a simultaneous radial position and tangential momentum. The cross product of its radius and momentum dictates this uniform circular motion possesses a non-zero orbital angular momentum. However, in the ground state of a hydrogen atom, the orbital angular momentum is exactly 0. An electron cannot have 0 angular momentum while it is physically orbiting at a fixed distance from the center. While the most probable distance for the electron is the Bohr radius, the electron is not moving along a specific physical path. The orbitals used in chemistry are statistical maps of probability, not tracks or orbits in the classical sense. The lack of simultaneous position and momentum means that for the electron, the very concept of an orbit does not exist. The paradox of wave-particle duality is a symptom of forcing microscopic objects into macroscopic categories. We have spent centuries sorting the world into particles, which are localized and rigid, or waves, which are undulating and diffused. An electron possesses properties of both, depending on how we probe it. Attempting to bridge this with new words like wavicle fails because it still relies on these exclusive macroscopic bins. Instead, we use the state vector. This is a mathematical object that encodes the system's entire configuration as a set of probability amplitudes. By calculating the state vector, we can predict every physical outcome without the ambiguity of everyday language. This raises the question of where the quantum domain ends and the classical world begins. There is no sharp boundary. The transition is a diffuse gradient, where quantum effects become less significant as the scale of the object increases. Classical mechanics is a low-resolution approximation of a quantum universe. It is the result of working at energy scales where Planck's constant is effectively negligible. Navigating physics requires moving past macro-scale intuition and adapting the strict logic of the mathematical state. Even the state vector is an incomplete framework when pushed to the absolute limits of space and time. Our most powerful accelerators can probe distances down to 10 to the negative 18 meters, the current frontier of human experimental evidence. The fundamental laws of our universe are defined by three constants: the quantum of action, the speed of light, and the gravitational constant. Combining these reveals the Planck length and the Planck time, scales of 10 to the negative 35 meters and 10 to the negative 42 seconds. 17 orders of magnitude separate our best experiments from the Planck scale. This is a vast region where the laws of quantum gravity are still unknown. At these extreme depths, our current understanding suggests that the continuous nature of space and time likely breaks down entirely. Physics is not a static collection of axioms, but an island of knowledge in a sea of ignorance. Every new discovery only increases the length of the shoreline.